let's move on to what is known as a Gaussian process. Okay. Gaussian processes. Okay, so this is an important topic, but some of the things I'll skip because it involves Fourier transform and Fourier series, especially, which I'm assuming that you know. So I'll leave it as some of the aspects as a homework problem. So you have to figure that out. Okay, so what is a Gaussian process? So you know that any stochastic process is a collection, right? Xt such that T belongs to some set T. That is it's a stochastic process. When do you say that it's a Gaussian process? Meaning a special kind of stochastic processes called Gaussian processes. When do you say that? So let's define it this way. So essentially, if you look at, you fix, let's say this is your time axis, think of T as time. You pick certain time instance, k of them, okay, t1, t2, t3, t4, and so on, k of them. And if you look at x of t1, x of t2, x of t3, and so on, x of tk, those are random variables. A collection would be a random vector. So if that random vector is a jointly Gaussian distributed, then we say that no matter what k and what these instances are, then we say that the process is a Gaussian process. Okay, we say that x of t, okay, so t belonging to, let's say, some t is a Gaussian process if for any k belonging to n, that means you take any integer, okay, and all choices of epochs, all choices of time instance, sorry, I'll call it as epoch or time instance. I'll use the terminology in the book. It's epochs. Epochs. What are those epochs? T1, T2, etc. Tk. So these are epochs. That is the time instance. Okay. If you look at x of T1, x of T2, etc., x of Tk is jointly Gaussian. Okay, is that fine? Any questions? You need to understand this, pretty well. So, any questions? Yes. Any questions?
So here, this is same as the one we defined for converting joint like Gaussian vector to Gaussian random variable.
No. See, the flow was this, right? So we introduced what is known as Gaussian random variable, okay, and then we move to what is known as Gaussian random vector, right? That is basically you give x1 through xn, it's called jointly Gaussian if any linear combination is a Gaussian random variable, right? That's how we moved, and then we looked at joint distributions and so on. But now, if you have I have to define what is known as a Gaussian processes. So the way to do that is somehow convert, this is like think of it as a continuous time process. Think of speech processes, speech signal, right? Well, it's not really a Gaussian process, but the noise in the speech process, for example, let's say you speak and then it gets converted into electrical signal and then noise gets added. So you can think of that process as a Gaussian process, meaning, well, how do you define that? So you don't know how to define some function as Gaussian, right? But you know how to define a bunch of random variables as jointly Gaussian. The way you do that is convert something that you don't know into something that you know. How do you do that? Sample. You take k and sample them, you get k random variables, you say that it's jointly Gaussian. Is that fine?
Yes, sir. So like
Right?
in
Hmm.
so like in random vector,
Hmm.
there are random variables x1, x2 up to xn. So
Huh.
here t1, t2 is different, and we are substituting like tx1 tx2, sorry, xt1 xt2 and something like that.
Yeah, it's like this. So, for example, I can think of it as like this, right? So you have a signal like this, which is Gaussian. So let's say x of t, and okay, so let's say this is your time axis, okay, and you are taking time instance. Let's say t1 is this, t2 is this, t3 is this, t4 is this, t5 is this, and so on, okay. And then you are looking at the amplitudes. Those I will call it as x of t1, x of t2, and so on, okay, and so on, right? So these x of t1, x of t2, and so on, x of tk are random. It corresponds. It's a random vector, right? For a fixed t1 through tk and k. If I fix k and t1 through tk, I'll get x of t1 through x of tk, which is a random vector. If that random vector is a Gaussian random vector, no matter what k is and where you pick these t1 through tk, then we say that the process is a Gaussian process. Okay, it's kind of weird in the sense we don't know how to generate this kind of a process, but we started out by saying, well, this is what I call a Gaussian process. We need to investigate whether this makes sense or not, right? I mean, if such a process does not exist and you may not be able to construct it, then the whole exercise is useless, right? So what we are going to do is we'll study a few other things and we'll see how to construct such a thing. Okay, did I answer your question?
Yes, sir. Yes, sir.
Okay.
So, sir,
Huh.
one more thing. So this x1, xt1, xt2, this will follow a Gaussian distribution.
Yes, so jointly Gaussian. What do you mean by jointly Gaussian? You have to specify two things, right? It's a the mean vector and the covariance, right? So that means if I specify these two things, then the entire joint distribution is known. Do you agree?
Yes, sir.
That's why Gaussian is beautiful, right? So you just need to know only two. It's beautiful for other reasons also. We'll see what those reasons are. But yeah, so this is what it is, right? Okay. So
So,
let's
sir,
look
Yes,
at
sir.
yes.
so here xt1 and t2 are random variables, right?
X
Individually,
of t1, x of t2, yes, they are random variables.
and they are Gaussian random variable.
Yes, so it is jointly Gaussian, so it has to be Gaussian. Can you prove that x1 through xn is jointly Gaussian? Can you prove that x1 is also Gaussian?
We take all the other things as zero.
Ah, exactly, right? Yeah, in your linear combination, you take 1 comma 0 comma 0 and you use that as a linear combination. Then you will get x1. x1 by definition is a Gaussian random variable. Yes, you are right.
Is it both ways, sir?
Meaning?
I mean, jointly Gaussian implies each is
Yeah, you have proved that now, right?
yeah,
Each
correct.
one is Gaussian. So you yourself have proved that, yes. Okay. Any question? Any other question?